we're going to have 4 lectures this, until the end of this day, starting with the upcoming presentation on introduction to Android security issues. But before that, let me just run you through a couple of quick points. First of all, there's an announcement that the ASC workshop, there's a training for ASC ISO 27000 security that has been moved to 3 p.m. So any of you who wanted to participate in that workshop, it starts at 3 p.m. in the Bobek Hall. Again, as in the morning, I urge everyone or try to encourage everyone to send your CVs to cv@hacktivity.com until next Sunday. That can get you a good job at one of the partners of Hacktivity for whom these CVs are going to be sent out, but it can also get you in for next year's Hacktivity. They're going to, there are 10 tickets to take away with that. Also, if you're thirsty, you can grab a free glass to use in the leisure zone at the RRC stand just outside here, or you can fill a hacker quiz and get free pogačo and food at the Vodafone Center in the first floor. Okay, so on to the afternoon session. We're going to have a presentation by Antonio Barresi and Peter Somogyvari. Antonio Barresi, after graduating, started to work as an IT risk officer for a Swiss financial institute, where he performed IT risk assessments and technical security audits for business-critical applications and infrastructure components. In June 2011, Antonio joined Ad Novum Informatik AG as a software engineer, where he works on security-related projects. Peter Somogyvari had a special interest in information security auditing and also in assembly programming as a low-level approach to getting a deeper understanding of how malicious software works. This year, he joined Ad Novum Hungary as a junior software engineer, and they're going to give an introduction to Android security issues. So the floor is yours.
So, do you hear me? Oh, perfect. So, hi everyone and welcome to our Android security presentation. So before we start, I would like to tell you what you can expect of today's talk. So as the name suggests, it's going to be an introduction, but it's going to be a rather technical introduction. The problem with security is always, if you would like to understand something and look at some cool stuff, you always have to look into the details. So what we're going to do is the following. We will have a first half where we just will talk a little bit about some basics. So we'll look at the Android security permission model, but we're not going too deep into the details. So it's rather scratching on the surface. And in the second part, we're going to show how to exploit memory corruption vulnerabilities on Android ARM devices. But still, we don't expect you to have any previous knowledge. We are trying to explain everything, but still you should have some technical background. So we were introduced already. Here is the outline. First part, Android security basics, and the second part, Android software security. And we will also have a demo in the second part. So before we start with Android, just some general thoughts on mobile security. Everyone talks about mobile security, but basically it's always the same, right? It's always about confidentiality, integrity, availability, authorizing, authenticating people, and so on. What has changed in the mobile world is pretty sure the threat scenario. So if you look or if you think of your client workstation within your company's network, it's a pretty safe place there. So your client workstation operates in a network where it can trust all the participants. The network is managed. It has some, maybe there is even intrusion detection and intrusion prevention systems. There is a perimeter, there are firewalls, and there is proven antivirus software, and so on. If you look at the same things in the smartphone world, so it looks pretty scary, right? Because a smartphone basically cannot trust anyone. It's most of the time connected to people or to devices it cannot trust, for example, Wi-Fi access points. It's easy to steal a smartphone or to destroy it or to lose it. And the last person probably you can trust is the user, because you can't trust into the user's judgment. He will basically install everything if he wants it, even if it asks for all permissions. So the smartphone world is somehow a little bit different than what we had before. And if you think about the data that is stored on smartphones, it doesn't make life easier. Basically, nowadays, you have everything on your smartphone. All the data you had I don't know, some years ago on your desktop and much, much more. So if I have your smartphone and all the data, I basically know everything about you. So as said, it's a technical talk. So let's look at the Android platform first, but as said, very quickly. So that's basically the picture you see in every Android presentation that is a little bit technical. So if you don't know Android, Android is a Linux-based operating system optimized for mobile devices. We have the Linux kernel at the bottom that interfaces the hardware. Then we have the native layer with all the libraries, so that's all native code. There is a libc, it's not GNU-libc, it's another libc, but basically just native code. And then there is the runtime, the so-called Dalvik virtual machine. That's where all the apps run. And on top of that, everything else runs in Dalvik, and you have the application framework. These are, let's say, more components that are system near, for example, a content provider for your contacts that manages all your contacts or your SMSs. And on top of that, you have all the applications that you can exchange. So you can, if you want, you can just have another SMS application. You don't have to use the one that is already on the device. So now let's look how an app comes to the system. So basically an app is an APK package. If you are a Java programmer, so it's like a jar package. The only difference is that you have one classes file. That's the classes.dex file. Within that you have all the logic. And that's Dalvik VM bytecode. And then there are some hashes and some signed hashes to make sure that the package, so that the integrity of the package is preserved. And if you install an app, the signature is checked, but one thing you will note now is that it's always self-signed. So in the Apple world, for example, you need a developer certificate, so you have somehow to prove that you're trustworthy, and then you can sign some packages, and it has any way to go through the App Store. In Android, it works differently. So anyone can just have a self-signed certificate and sign any package. And if you have the right option set in the settings, you can just install it on your device. So in Android, a signed package does mean that if you have application A and application B, it comes from the same developer. It doesn't mean that the developer is trustworthy. And then the signature, it's checked at installation time, so if you find some way to change it on this file system, if it's already installed, that's going to be, you can manage to do that. And during installation, you will always have a user assigned to the app. So now we see the first, let's say, things connecting to the Linux operating system. So an app will always have also a Linux system user, and that gets assigned at installation time. And what also every app gets is some region within the file system. So in that case, it's data, and then the package name. So every app has its own file system region. So we now know how an app comes to the system. Let's see where it runs. As said, every app has an own Linux user. So what basically happens is that there will be a process for every app, and within that Linux process, your app, or let's say your Dalvik VM instance will run, and within that, your app. So basically, you map apps to processes. And as said, so most apps are Java-based, but you can also have native apps. So especially from version 2.3, you can have entirely native apps. So when you tap on one of your icons and you start an app, there is no execv system call executed. So there is no binary that gets loaded, right? So what happens is there is a so-called zygote process. This is a process that gets started after boot time, and it just waits. And as soon as someone will start another app, it forks itself, and within this forked image of zygote, the app will run. And of course, the user permissions will be adapted accordingly. So now that's basically a little bit the overview, how you can imagine an app runs on a device. Let's look at the Android permission model. So that's something that most users probably know. If you install an app, you get asked for permissions, right? And exactly these permissions, they're within the Android manifest file that comes with the APK package. So if I'm an app developer, I develop an app, I say I need internet access, I write it into the manifest, and the user gets prompted to accept it. But the Android permission model allows more. So if I'm an app developer, I can even say I would like to have a known permission that other apps have to have, and when someone would like to start one of my components, it has to have this permission. So it's pretty flexible. The next thing that is pretty security related is, of course, the Android sandbox. And here's, let's say, the special thing about the Android sandbox. It's not implemented at one place. So basically, it consists of the Android permission model. So if you would like to access some SMS data, you need the permission, and everything happens on the Java layer. But if you, let's say, want to access a file on the file system, then the Linux file permissions kick in, and that's where the authorization is done. And the other thing that also is done is when you access network, for example, you need a specific group to be able to open some sockets. So here's the example. So let's say you install an app, and the app asks for the internet permissions. What happens is, in the platform.xml files, it says that every app with internet permissions will be in the inet group. So the user which will be created will also be assigned to this group. And within the Linux kernel, we will have this check. So the inet create function gets called when you open a socket for the inet family. And within that, they will check if you are really in that group or not, and depending on that, you can open the socket or not. So you see, so the Android sandbox is somehow distributed or is implemented in different areas and different parts of the operating system. So that's basically it for the first basic introduction. I would like to give over to Peter, so he will tell you a little bit more about data security.
Hey guys, can you hear me? Okay. So about device and data security, first of all, I just wanted to show you some interesting stuff. So basically that's it. And the question is what the manufacturers and the Android operating system does for you to protect your device and your data. First of all, you can use the screen lock mechanism with numerous methods. And there's the bootloader, it's locked by default. You can of course unlock it. I will explain it later. And the other thing is that you cannot run ADB, the Android debug bridge, with root privileges by default on a production device. ADB is simply a binary, and you can issue commands with it to your phone from a host machine of yours. And if you choose to lock your device to the screen lock, either with a PIN or a passcode, it will get hashed in a way. It will get concatenated by the salt and then hashed twice, and the results of the hashes will get concatenated again. It will get stored in specific places in your device. That's the important part, that it will be on your device. And the place where it gets installed depends on the OS version, because Jelly Bean introduced some new database to store the salt. Well, if you somehow able to obtain the salt and the hash code of your passcode, then you can just brute force it, as we mentioned in some example. Another thing to mention is the policies.xml, which contains the strength of your password. There are other restrictions which you may have to obey when giving one. Here we did some interesting statistics about how it can brute force, and there are other questions. Should you use GPU computing power to break it, or just rainbow tables? It's an interesting question. The boot process is really a critical part, because at boot time, you will have the bootloader load an image, and if it's unlogged, it won't check against the signatures of that image you are booting. So basically, you could just put in a custom recovery image, if it's unlogged, and dump all the physical data of the user's device. So if I just found your phone on the street, it doesn't matter if it's logged or not, I mean the screen lock. If you have your bootloader unlogged, then I will gain access to all your data and I could break it offline. Routing. Well, routing is about gaining access to root privileges. You can run apps with root privileges, which you can't normally do in the stock ROMs. Well, that's all about routing. Storage encryption is introduced in 3.4, and it uses your passcode, which you provided earlier for the screen look itself, to derive a symmetric key from it for the specific algorithm, which will then encrypt your storage. The place where this could be improved is that it doesn't include some hardware support. And Apple made it a little bit more strong with built-in hardware encryption support on their devices. And I'm going to talk about the attack path. So if I want to get your data stolen, what choices do I have? First of all, there's the, let's say, remote way of it, where I could place a malicious app, which asks for too many permissions, and you will give it them because you want to get the default use cases of the application, and then I will steal your data. Another scenario would be to exploit another application which has security holes introduced in itself. Antonio will show you an example of that. And also, there are the physical parts, where I could try to run ADB on your device. If you left open the USB debugging enabled check, then I could install an application on your device. And by default, I would have all the permissions an application can have on the Android OS. If the ADB is not running, I could still check if your bootloader is logged or not. And if it's not logged, I could just do a physical raw data dump and break. If you enable storage encryption, then I would have to still break it offline. But there I could have, let's say, much more computation power, sorry. And another way to do it is just to get specific hardwares to extract your data from the NAND flash or the SD card, let's say, without even turning your device on. And again, if it's encrypted, I could just break it offline then. So what's our conclusion here? Is that passcode is really useful, but you should do a longer one and never trust it fully. The other thing is that the storage encryption is good, but it still could be improved to have hardware support. And also, if you have a mission-critical application which needs to protect the data it produces, you should introduce your own encryption algorithms or any solution to protect it. And you should not store your keys on the device. Or you should just store it in the user's head or on some third-party servers you want. And that's it for me. Thanks.
So basically, that was the first part. Do you hear me? Okay. So now we're going to look at the second part. So that's the more detailed and more advanced part, but still we don't require any previous knowledge. So what we're going to look at is, we're going to look at how well are the processes running on the native layer protected against the exploitation of memory corruption vulnerabilities. So the kind of buffer overflow, format string vulnerability stuff. So in case you don't know what a memory corruption vulnerability is, it's basically a bug where an attacker can corrupt some kind of memory or some parts of the memory of a running process. And there are some interesting parts that can be corrupted, right? So maybe there is some interesting data that could change the behavior of the application so that the attacker gains some additional knowledge or an advantage. Or there are maybe some interesting pointers so that you can hijack the control flow. So in the last 10, 15 years, a lot of exploit mitigation techniques were implemented in modern operating systems. So the most effective ones or the most revolutionary ones are listed here. There are others implemented in Android, so you can go and look into the documentation. So there is a list that explains what kind of exploit mitigation techniques are implemented in different versions. But we would like to focus on these. And the next step will be, we're going to show you a vulnerable app, and we're going to show you how you can exploit this vulnerable app on 2.3, so on Android Gingerbread. That has this protection mechanisms enabled. And then we are also going to see how you can do that on the newer Android versions. So that's the vulnerable app. So we noticed 20 minutes ago that it's not so good to read. So basically what it does is it opens a network a socket, it listens to port 7100, it waits for some data. As soon as it gets some data, it writes the data back. And the handling is, will be done in two functions. So there will be the read from socket function that reads the data, and then there will be the echo function that will write the data back to a socket. Here it's how it looks like in action. So basically, we will have our computer, we will connect to port 7100, and it will get some data, and it will just write the data back. So you will say, of course, that's a pretty silly app, and you're right, so it doesn't do much. But the thing here is we just wanted to have a vulnerable app to show you the concept behind it. So basically think of any app that takes some user data, does some processing, maybe there will be some vulnerability in it, and then depending on the processing, it produces an output. So if you look at the code more closely, you will notice some things. So first of all, it will read 1024 bytes into a buffer that is just 512 bytes big. So that's the classical case of stack-based buffer overflow. And the echo function itself, it will use nsprintf and take whatever the user replies. So basically, we have a format string vulnerability there. If you don't know what it is, I will try to explain it here on a architecture independent level. So most computer architectures, you will have a stack for each function. So as soon as you enter a function, there will be a stack allocated, and within that stack, the function will have some variables. And if you have a buffer there and some operation that takes some data and writes to that buffer, and if it isn't careful enough that it doesn't overflow the buffer, you basically can overflow whatever is behind it. And in a lot of cases, you have very interesting data behind it. Maybe some variables that are not that important, but on a lot of architectures, you have some return addresses on the stack. So on Intel, for example, if you have a call instruction, the return address, so the instruction that comes next, will be pushed on the stack. And that's basically also there on the stack. And if you know how far it is, you can basically overflow it. And as soon as the function returns, it will return to that address, and basically you can hijack the control flow like that. So the next thing we saw before, we also have a format string vulnerability. So if you don't know what it is, basically it's some kind of injection vulnerability. So when you look at the printf family, there is a family of functions. So probably if you are a C programmer, you know them. So if not, it basically takes some strings and puts the strings somewhere else. In that case, printf takes some strings and puts it on the console. And if you don't call it carefully, you can basically read out values in the process memory, because that's what happens. You have a printf function, and you have a format placeholder. And to that function, you pass a number. And the output of this function call will just be the text, and it will replace the formal placeholder with the argument you passed to it. If you forget to pass any arguments, basically printf or all the printf functions, they will assume that an argument was passed. So it will just take the next arguments and put it to the placeholders. So in that case, you can just, if you're able to control this string, including the placeholders, you can just instruct printf to take some values from the stack and print it out, or in case of sprintf, print it into another string. And there are some other interesting format placeholders, like the %n. So that one is a little bit differently. So as soon as printf sees %n, it will write the number of outputted bytes to an address that it finds on the stack. But we're not going to use that one. So here again, a vulnerable native app. We have the stack-based buffer overflow, and we are going to use that one to hijack the control flow. And then we have the format string vulnerability, and we're going to use that one to inspect the memory. And before we really can get started, some R machine language basics, because we're going to see some R machine language. So ARM is a 32-bit RISC architecture, and it has 16 visible registers, R0 till R15. And 3 of them are special purpose. So there is the stack pointer, R13, there is the link register, R14, and R15 is the program counter. Stack pointer is stack pointer, points to the stack, obviously. The link register will hold the return address during function calls. So that's a little bit different than Intel, where you push it on the stack. And the PC, the program counter, is basically the address that it gets executed next. That's the instruction pointer in Intel. And the cool thing about ARM is you can read and write PC like any other register. That's differently in Intel, right? You can't just put some value into the instruction pointer. So something that is important, especially for write exploits, is you have to know the calling convention if you call some other functions. So in ARM, the calling convention looks like this. You pass the first 4 arguments within the register and everything, so if you need more, you pass it on the stack. So that's a bit different than Intel. There you pass everything on the stack. Before you call the function, you push them on the stack and then you go to the function. There's some other detail in ARM. So ARM supports different kind of instruction sets. So there is the ARM normal mode, that's a 32-bit opcode instruction set, and there is the thumb mode. That's a 16-bit opcode instruction set. And the reason for that is ARM is used in a lot of memory-critical devices. So with that, you can have much more code density. So if you use thumb, if it's enough for you, you can have much more instructions in the same amount of memory. And the transition between these modes happens with the last significant bit. So if you branch to some address, if the last significant bit is 1, it will change to thumb mode, and else you are using ARM mode. So just to get warm up a little bit, some instructions. So we have the push instruction in ARM, basically pushes R4 and first LR and then R4 onto the stack. We have the load instruction that will load register R3 with the value at address PC plus 60 decimal. That's the branch, so that the call instruction. So it will call this address and it will put the return address into the linked register. And that's the move address, pretty obvious. There's the store address where you store the value within R3 at this address. So basically, some value gets stored on the stack. And then there are arithmetic instructions. Okay, so we implemented our native vulnerable app, and we wanted to exploit it. And we wanted to look at it on a real production device, because if you use the emulator, it's a little bit different there. So we bought a device. So it's a 2.3.4 Samsung Android device. It's called Samsung Galaxy Mini. And just remember that still nowadays 56% of all Android devices are gingerbread, so 2.3 devices. So that's pretty representative. And one little side note, when we bought the device, we checked out the settings, and the funny thing was that debug mode was enabled by default. So somehow the carrier's stock image has debug mode enabled by default, and that's very bad, as we saw before, because you can basically push an application to it with all the permissions, and with that you can read out the stuff. So let's look again at the vulnerabilities. So we have the stack-based buffer overflow and the format string vulnerability. So that's our plan. We will overflow the buffer, and we will overflow the value on the stack where LR is pushed to. So if you look at the function enter of read from socket, where you have the stack-based buffer overflow, you will notice that the first thing the function does, it will push LR to the stack and then R4. And at function leave, it will read R4, pop it, and it will put the value of LR that we had on the stack into the program counter. So execution can continue there. So that's pretty much similar like in Intel, just with the difference that you have a dedicated return instruction that takes the value from the stack. So our plan is to overflow the buffer and also overflow the value LR, so the link register value that got pushed before, with an address to somewhere with code that we would like to execute. And in that case, there will be our shell code that we would like to put on the stack. So like this. So when you try this, you will notice it will not work. And the reason for that, we saw it in the overview at the beginning with all the exploit mitigation techniques that are implemented. There is stack protection implemented on Android 2.3, no, even on Android 1.5. So they all have stack protection implemented. And what stack protection does is it compiles some code into the binary, and as soon as you enter a function, it will put some value onto the stack after it pushed the link register and R4 onto the stack, and this value is random. And at function exit, it will compare two values, so it basically puts one of the values, so the random guard into one register, and the value of the random guard that it expects to the other register, and it will compare them. And if they're not the same, it will just go to an exit function. So it will call some cleanup function, and then it will exit. So that's the stack protection. So if you overflow the buffer, you have to also overflow the random guard if you would like to reach the return address. And that's what it tries to detect. So if you try it, that's what happens. So we try to overflow the buffer with more than 512 bytes. And if you look at the log output, you will see that the app process exits, and you will see this nice message, stack corruption detected. So that's not going to work. So somehow we have to bypass that. And because the vulnerable app is very, very vulnerable, we have a format string vulnerability, and with that we can read out values on the stack. And the thing to notice here is that the echo function comes after the read from socket function, and it allocates more on the stack than the read from socket function. So somewhere also from the stack pointer of the echo function upwards, there will be the random guard somewhere, because that's not going to be overwritten. So the idea here is to somehow find that value and read it out. And you can do that if you use the format string vulnerability and pass the right format placeholders to it. So if you pass this, so if you type this to the app, it will give you some values, and that one is our random guard. So you can try that out with a debugger, and then you will find it. Another thing to notice is that we have another interesting value on the stack, and that's basically a value that points to the stack. And the cool thing here is we can use that to calculate the exact address of the read from socket receive buffer. Normally stacks, although in 2.3 it's not randomized, we saw that address-based layout randomization will just be implemented from 4.0 on. Although we don't have that, the stack location is always dynamic, so it depends on the runtime. Therefore, with that, we can calculate the exact address too. So what we have now is we have the random guard that we need to bypass stack protection, and we found an address that points to the stack. And by having the right diff, we can always find out what the receive buffer address is in read from socket. So let's try it again, right? So let's put the address of the shellcode that we calculate and the random guard on the stack when we overflow it. And now we should be able to somehow take over control. As soon as the function leave pop instruction happens, we should execute at that address. This is not going to work either because of the non-executable stack we saw. So the stack is normally not executable since 2.3. And the heap is also not executable. So basically, we are now able to hijack the control flow, but we are not able to execute the code on the stack that we placed there. So if you look at the memory maps, you will see that the stack region will have read-write privileges, so no execution privileges. So we have to circumvent or bypass that somehow. So what we know now, we can hijack the control flow, and we cannot execute the stuff on the stack. But there is much more within the process virtual address space that we can execute, because there are a lot of things there that are mapped executable. For example, system, the libc, of course, right, and other libraries. But what we're going to do now is that we're going to use Return-to-libc. So that's also pretty known, right? It's not Android specific, but we're going to use it now in Android. So the idea is to use some libc function, and more specifically, we're going to use mprotect. So mprotect is a function where it's a system call, and you can change the privileges or the permissions of the memory mappings. So if you have a memory area that is just read-writable, you can call mprotect and tell it, please make it executable. That's what we are going to do. And it works because it's a Linux kernel and there is no restriction in Android to the mprotect function. So we can just do that. But if you want to do it, we have to be a little bit clever, because as we saw before, the call convention on ARM is you pass the arguments on the registers. So you don't have it on the stack, so you pass it through the registers. So we somehow, before we can call mprotect, we need to put the right parameter, the right arguments into the appropriate register. So in that case, it's R0, R1, and R2. So R0 has to be the aligned address of the stack, then the size, and then the new permissions. And if we manage to do that and call mprotect, after that call, our stack will be executable again. So at the end of mprotect, there will be this instruction, as every function. We will return at the link register value, right? And that's pretty important, because if we call mprotect, after that we lost control, right? So mprotect will do whatever it has to do, and then it will just jump back to LR. So the next thing we have to make sure is that LR has the right value, exactly the value of our shellcode on the stack. So mprotect will then make the stack executable, put at the end the value of the shellcode, so the address of the shellcode within LR to the program counter, and we are then able to execute our shellcode on the stack. So to do that, we first have to find a way with some instructions to fill up these registers with the right values, right? And what you can do, you can just, with a debugger, or can just disassemble some libraries. And in that case, we looked at libc. You can just look for some cool instructions that will help you do that. And you will pretty soon find some suitable instructions. One instruction that we found was this one. So that will basically load multiple values from the stack into R0, R1, R2, R6, stack pointer, link register, and the program counter. Basically, we can do everything. We can fill up the registers, and we are still in control of the execution flow. So that's what we're going to use. So when we overflow the buffer, we're going to make sure that it looks like this. So we will need the random guard to bypass stack protection. We'll need the address of the load multiple instruction as the next instruction that is going to be executed. Then there is some value we don't care, because this load instruction will first increment the pointer that it found, so the stack pointer with 4, and then we have just some values that we can just put in there that it's not going to be relevant. And from then on, it will read the next value into R0, so that's going to be the address of the stack, because that's the first argument to mprotect. Then the size that we have to pass to mprotect, the permissions, so in that case, read, write, execute, and another value, R6, we don't care about that. We can even adjust the stack pointer, and then the values for the link register that has to point now to our shellcode, and the one for the next program counter, which is mprotect, because that's what we would like to execute next. And if you do that, it will work. So basically with that, you can bypass stack protection and the non-executable stack. And after that, you can execute whatever you want on the stack. And the nice thing is mprotect is pretty helpful, right? I mean, it does all we want. So we didn't speak about the shellcode. That's basically the part that we want to inject and that we want to execute. We're not going to speak about it. You can just use Metasploit, for example. It has some exploits for ARM Linux, so you can use them. We used the ones that we're going to show you in the demo will just be the bind shell, where we will open a port and listen to it and then present the shell to that port. So now it's demo time. So basically, here is the device, and there is the vulnerable app installed here. And we have here a private Wi-Fi. So basically, do you see that? Okay, so I should be able to ping the device Yes. So I'm pinging now the device. I just started the vulnerable app, so you don't see anything. So basically, it listens at port 7100. So here is our app, and we can just say hello, right? And it will just print it back. So that's it. Here is the exploit we wrote, so we are not going to look into all the details, but so it's not, yeah, you can read it. So basically we will first exploit here the format string vulnerability. We will get the right values, and then we will connect again. First we will construct the buffer accordingly, and then we will connect again and, where is it? Here and write the exploit buffer. So after that point, we should be able to execute code on the device. And what the shellcode will do, so that's how we will see if it worked or not. It will open port 4444, and we should be able to have a shell there. So if I do it now, nothing happens, so there is no one listening there, right? So let's execute. Oh, yeah. So it will do now everything we talked about before, right? And from now on, if it worked, we should be able to connect to it. And now we should have. We should, yeah. Yeah. So basically, you see that we connected to it, but it somehow doesn't print out back what ls puts out. So that's, we don't know yet why it's not that stable, but it works sometimes, and sometimes it doesn't. So we haven't debugged it yet. So that's not going to work. Can you just restart it? Okay. I will show you the other exploit we prepared. So in that case, we thought, okay, because it doesn't work that stable, we prepared another one with another shellcode. The other shellcode will just execute an application that is already on the device, and that will just play a sound, so you will hear it. But so I will continue with the presentation, and then we will do the demo later on. So one very, let's say, effective exploit mitigation technique, especially combined with non-executable memory areas, is address-based layout randomization. And that's basically one thing that was not that implemented that consequently from the beginning in Android. So here's a comparison. We exploited it on 2.3.4, and in Ice Cream Sandwich and Jelly Bean, you will have a little bit more protection. But the thing is, for Ice Cream Sandwich, you still have memory areas that are not randomized. So therefore, if you still have some code that you can, with addresses you can predict, it's not going to help you, right? But from Jelly Bean on, basically everything is randomized. And then it gets very difficult to exploit it. Our vulnerable app is even exploitable on Ice Cream Sandwich and Jelly Bean, because it has a format string vulnerability and a stack-based buffer also. But so even if you would have, let's say, libc totally randomized, you could still find some value that points to libc, so that you can calculate the randomized base address. But think about it. Let's say you have a vulnerability in the wild that, of course, is not that comfortable, right? So where you can't just read out some memory values. Then it's going to be very difficult, especially from Jelly Bean on, to somehow find the right addresses. So the conclusion there is, of course, on Jelly Bean on, so 4.1, it's much more difficult to exploit memory corruption vulnerabilities. And before that, it was a little bit easier. So that's for sure a pretty good improvement in Android. And I hope that you understand now also the background, so why that is so important and why it works so effective.